I'll be talking on a new topic, that is gas hydrates. So that has been considered as a fuel of the future in India. So ONGC and has worked a lot on that through NGHP, National Gas Hydrate Project. So I'll give you a glimpse of that. I have working on it since last 1 decade, and now we are using it for CO2 capture and sequestration applications. Yeah, thank you. Okay, so everyone know that the CO2, how much CO2 we are releasing, right? So globally, it's 37 gigaton or billion tons of CO2. That's a huge amount. In India is emitting around 3 gigaton or 3 billion tons of CO2. So how we can, yeah. So to solve this problem of CO2 emission, so the most adopted technology, as Atulji mentioned, the CCUS. So where we have to capture the CO2 from a point source, we have to transport it. So then the option is either we have to utilize it to convert CO2 to various chemicals, or dump it to sequester it. For sequestration, there are lot of cost involved. If you see the total process involves more than $100 per ton of CO2 is required, right? As I mentioned, we are working on gas hydrate that has been considered a fuel of the future in India. We see in India we have almost more than 800 trillion cubic of natural gas in the form of gas hydrates. That's a very good opportunity for India to recover this natural gas to increase our gas-based economy. And so gas hydrate is like just water and gas. So that is a natural process. Naturally, methane has been captured in the form of these calathrate hydrates. Looks like ice, right? So we are using this process of methane hydrate. Okay, so we are using this gas hydrate process for CO2 capture application. As I mentioned, this is a process of water and gas only. So we optimize the pressure and temperature condition. We can use it for CO2 capture applications, right? From pre-combustion or post-combustion CO2 capture. So these are the conditions that we can optimize to form this CO2 hydrate, and which this is a very simple process. Through this gas hydrate process, in 2 stages, we can get almost pure 99% of pure CO2 through CO2 hydrate formation. And the process is based on the Selexol, Rectisol. The capture efficiency is very good and comparable. If we'll do it at large scale, so we can get the economic. So now if we move the CO2 sequestration, as I mentioned, the amount is huge. After capturing, then the question comes what to do with this captured CO2. So we can dump it inside the geological formations. So similarly, as I mentioned, it's a natural process. So we can use the same gas hydrate, CO2 gas hydrate formation inside the subsea sediments, inside the subsea wells, and can form CO2 hydrate, and we can sequester this CO2 permanently. Okay, and based on that, we have done a project in collaboration with CSIR NIO. We got a lot of data from CSIR NIO to understand that what are the locations, where is the conditions where we can sequester the CO2 inside the Arabian Sea sediments, or the other side, the KG Basin sediments. We worked on a lot of the challenges that was associated with the CO2 sequestration, like geological suitability, the rate of hydrate formation, its stability, and its impact on the aquatic life. Right? So we initially started in lab scale setup. So we designed a very small high pressure reactor setup, optimized the conditions exactly similar that we have inside the subsea, the high pressure and low temperature condition. We form the CO2 hydrate in lab. We use the actual sediments that was collected from the Arabian Sea at different locations to understand how much CO2 we can sequester in such type of sediments. So if we see the very preliminary data, So if we just use the sediment and the DI water, so we are converting almost 80% water to hydrate. But when we are using the saline water, that is the actual sea water, which is highly saline, you can consider around 3.5 weight% of salts are there, it's significantly reduced, and you can say almost just 20% conversion we are getting in almost 24 hours in a very small setup. Then we try to improve the kinetics, how we can get this better conversion in lesser time, right? Then we use various additives like biocompatible additives like leucine, amino acids we used, and we improved the kinetics. You can see just in 2 hours, instead of 24 hours, now we are getting the similar type of conversion in just 2 hours. So now we improved the kinetics so fast that immediately you just mix the, pressurize the reactor with CO2, your water will convert into solid CO2 hydrate, which looks like ice in just 2 hours. So we did a lot of optimizations and all. Then now the question comes, can we move from lab to the field? So we worked on a CSIR CCUS mission. So we are getting very good support from the government. Again, with the help with CSIR NIO Goa. So we designed a big pilot scale setup. We collected a lot of cores from the Arabian Sea sediments. We characterized them to understand the suitability of these sediments and the location where we can inject the CO2 in such type of sediments. And also the important point, the CO2 seepage and the impact of CO2 on the aquatic life or on the microorganism. Can we do it at large scale? It will not impact the aquatic life. So all this work we have completed through the CSIR CCUS mission. Yeah, so that's it from my side. So I'm sorry it was so quick because of time constraint. So you can discuss with me if you have any question regarding the CO2 capture and sequestration process. Yeah, thank you so much. I would like to acknowledge UPES, our VC, Sunil Ray sir. He is here. He will be talking in next session about the research, what type of research we are doing. Our president, Dr. Ram Sharma, and Prof, Dr. Jay. Also would like to acknowledge CSR IIP, where I was working, because I have been a part of the CSIR CCUS mission in this project, and my PhD student, the funding agency, DST, and the CSIR. Thank you so much.
Thank you, Professor Asheesh.